Hello, this is Tim Smith, the Academic Support Coordinator for St. John's River State College, St. Augustine campus. This lesson, Lines and Planes in Space, is designed as a study aid and supplement to the math tutoring services offered at St. John's River State College. It is recommended to view the videos Introduction to Vectors, the Dot Product, and the Cross Product prior to watching this video. In this video, we will discuss the equation of a line, parametric equations of a line, vector equation of a line, two lines skew, parallel, or intersecting, vector equations of a plane, and planes parallel or intersecting. In geometry, a line is an infinitely long object with no width in a space of 2, 3, or more dimensions. For any two distinct points, there is a unique line containing them. In space, let P be a point described by x sub 0, y sub 0, z sub 0, and Q described by x sub 1, y sub 1, z sub 1. These 2 points describe a unique line in space. We can also establish a vector PQ as x sub 1 minus x sub 0, y sub 1 minus y sub 0, z sub 1 minus z sub 0. Next, let D be a vector ABC parallel to the line described by the vector PQ. If two vectors are parallel, then they are scalar multiples of each other. The vector PQ equals T times the vector D. If the vector PQ is equal to T times D, then the vector x sub 1 minus x sub 0, y sub 1 minus y sub 0, z sub 1 minus z sub 0 equals T times the vector ABC. We can then separate the vector into its components to get x sub 1 minus x sub 0 equals A times T, y sub 1 minus y sub 0 equals B times T, and z sub 1 minus z sub 0 equals C times T. With each of these, we can solve for x sub 1, y sub 1, and z sub 1, giving us the parametric equations of a line. Going back, if we solve each equation for t, we can establish these equations as equal to each other. This gives us x sub 1 minus x sub 0 over A equals y sub 1 minus y sub 0 over B equals z sub 1 minus z sub 0 over C. This equation is called the symmetric equations of a line. Taking the same points P and Q from before, we establish a vector from the origin to P is r of 0 equals x sub 0 I plus y sub 0 j plus z sub 0 k. And the vector from the origin to Q is r of 1 equals x sub 1i plus y sub 1j plus z sub 1k. Applying the parametric equations of the line, we can generalize the vector function r of t equals x sub 0 plus at times I plus y sub 0 plus bt times j plus z sub 0 plus ct times k. If we distribute the parentheses, we can derive the vector equation of a line r of t equals r sub 0 plus t times the vector d, where d equals ai plus bj plus ck. For example, find the vector equation containing the point p sub 0 equals 1, negative 1, 3, and p sub 1 equals 4, 2, 1. We start with the vector equation of a line r of t equals r sub 0 plus t times d. In this case, d equals a vector from p sub 0 to p sub 1 equals x sub 1 minus x sub 0, y sub 1 minus y sub 0, z sub 1 minus z sub 0. We fill in the values for x, y, and z to arrive at d equals a vector 3, 3, negative 2, or 3i plus 3j minus 2k. This r sub 0 is I minus j plus 3k. Therefore, r of t equals I minus j plus 3k plus t times the quantity of 3i plus 3j minus 2k. Combining terms leads to the final vector 1 plus 3t times I minus 1 minus 3t times j plus 3 minus 2t times k. In another example, find the parametric equations of the line and the symmetric equations of the line containing the point 1, 2, 3, and in the direction of 2i minus j plus k. Remember the vector equation of the line. In this case, r sub 0 equals I plus 2j plus 3k, d equals 2I minus j plus k. Therefore, R of t equals I plus 2j plus 3k plus t times the quantity of 2I minus j plus k. We group like terms to arrive at 1 plus 2t times I plus 2 minus t times j plus 3 plus t times k. Therefore, the parametric equations are x equals 1 plus 2t, y equals 2 minus t, and z equals 3 plus t. Next, we solve each equation for t to get t equals x minus 1 over 2, t equals negative y plus 2, and t equals z minus 3. This gives us the symmetric equations of the line x minus 1 over 2 equals negative y plus 2 equals z minus 3. Are two lines parallel, intersecting, or skew? If two lines are parallel, then their direction vectors will be a multiple of each other. For example, if line L1 is described by the vector r sub 1 equals 2i plus 3j plus 4k, and L2 is described by the vector r sub 2 equals negative 4i minus 6j minus 8k, these two lines, L1 and L2, are parallel because r sub 2 equals negative 2 times r sub 1. Given two lines described by the vectors r sub 1 and r sub 2, if there exists a t sub 1 and a t sub 2 that make r sub 1 equal to r sub 2, then the lines intersect. If two lines are not parallel or intersecting, then they are askew. For example, determine whether the following lines intersect, are parallel, or skew. Line 1 is r sub 1 equals 4i plus 3j plus t sub 1 times the quantity of I minus j plus 6k. Line 2 is r sub 2 equals 4i plus 3j plus 2k plus t sub 2 times the quantity of I minus j minus 2k. The vectors of these two lines are not multiples of each other, so the lines are not parallel. We next ask if there is a t sub 1 and t sub 2 that would make r sub 1 equal to r sub 2. We start by setting the two lines equal to each other. Taking the I components, 4i plus t sub 1i equals 4i plus t sub 2i. This means t sub 1 equals t sub 2. Taking the j terms, 3j minus t sub 1j equals 3j minus t sub 2j. Therefore again, t sub 1 equals t sub 2. Finally, take the k terms. T sub 1 times 6k equals 2k minus t sub 2 times 2k. From the other components of the vector, we determined that t sub 1 equals t sub 2. Therefore, we replace t sub 2 with t sub 1 to get t sub 1 times 6k equals 2k minus t sub 1 times 2k. Next, add t sub 1 times 2k to both sides of the equation. Then factor t sub 1 from the two terms on the left side. Add 6k to 2k to get t sub 1 times 8k equals 2k. Divide both sides by ak to get t sub 1 equals 2k over ak, or 1/4. This means that the two lines intersect when t sub 1 equals t sub 2 equals 1/4. In geometry, a plane is a two-dimensional object in a space of 3 or more dimensions. In a three-dimensional space, a plane can be defined as the intersection of three distinct points, or an intersection of a point and a line. Using vectors, we can establish a plane as a vector r sub 0 being the vector from the origin to P, and r being the vector from the origin to Q. If we then establish a normal vector n, where n equals ai plus bj plus ck, and is perpendicular to the plane, then the vector pq times the dot product of n equals 0. The equation can then be expressed as x minus x sub 0 I plus y minus y sub 0 j plus z minus z sub 0 k times the dot product of ai plus bj plus ck equals 0. We take this dot product to get a times the quantity of x minus x sub 0 plus b times the quantity of y minus y sub 0 plus c times the quantity of z minus z sub 0 equals 0. We'll next distribute our parentheses. If we set D equal to A times X sub 0 plus B times Y sub 0 plus C times Z sub 0, then we get the general equation for the plane AX plus BY plus CZ equals D, where A, B, C, and D are real numbers, and the vector AI plus BJ plus CK is normal to the plane. For example, find the general equation of the plane containing the point 1, negative 1, 2, if the vector 2i minus j plus k is normal to the plane. We start with ax plus by plus cz equals d. The normal vector is 2i minus j plus k, and 2x minus y plus z equals d. We fill in the x, y, and z values from our point to get d equal to 5. Therefore, the general equation of the plane is 2x minus y plus z equals 5. In another example, find the general equation of a plane that contains the following 3 points. P sub 1 equals 1, 2, 1, P sub 2 equals 3, 2, 2, P sub 3 equals 4, negative 1, negative 1. We first start by establishing a vector v between P sub 1 and P sub 2, which would be 3 minus 1, 2 minus 2, and 2 minus 1, giving us the vector 2, 0, 1, or v equals 2i plus k. Next, we establish a vector w between points P sub 1 and P sub 3, or 4 minus 1, negative 1 minus 2, and negative 1 minus 1, or 3, negative 3, negative 2, or w equals 3i minus 3j minus 2k. Next, we find the normal vector to the plane by taking the cross product of v times w. We use a 3 by 3 determinant with the first row as ijk, the second row from v, 2, 0, 1, and the third row from w, 3, negative 3, negative 2. This equals the 3 2 by 2 determinants 0, 1, negative 3, negative 2 times I, minus the 2 by 2 determinant 2, 1, 3, negative 2 times j, plus the 2 by 2 determinant 2, 0, 3, negative 3 times k. This gives us 0 minus negative 3 times I, minus negative 4 minus 3 times j, plus negative 6 minus 0 times k, or a normal vector 3i plus 7j minus 6k. We next apply this vector and the point P sub 1 to the equation of a plane to get 3 times the quantity of x minus 1, plus 7 times the quantity of y minus 2, minus 6 times the quantity of z minus 1 equals 0. Distribute the parentheses, simplify, and move the integer to the other side of the equal sign to get the general equation of the plane 3x plus 7y minus 6z equals 11. Two distinct planes are parallel if they have parallel normal vectors. In other words, n sub 1 equals k times n sub 2 for k not equal to 0. If two planes have normal vectors that are not parallel, then the planes intersect in a line D equal to the cross product of n sub 1 times n sub 2. For example, evaluate the following planes. 3x minus 2y plus z equals negative 1, and 2x plus y minus 3z equals 4. The normal vector of the first plane, n sub 1, equals 3i minus 2j plus k. The normal vector for the second plane, n sub 2, equals 2i plus j minus 3k. First, we find the vector d by taking the cross product of n sub 1 times n sub 2. Using the 3 by 3 determinant, we fill in the first row with ijk. The second row gets the values from n sub 1, 3, negative 2, and 1. The third row from n sub 2, 2, 1, negative 3. This determinant is solved by the 3 2 by 2 determinants, negative 2, 1, 1, negative 3 times I, minus the 2 by 2 determinant 3, 1, 2, negative 3 times j, plus the 2 by 2 determinant 3, negative 2, 2, 1 times k. This gives us 6 minus 1 times I, minus negative 9 minus 2 times j, plus 3 minus negative 4 times k, or d equals 5i plus 11j plus 7k. Next, we find a point that intersects both planes. We do this by first setting z equal to 0. When applied to the original equations of the plane, we get 3x minus 2y equals -1, and 2x plus y equals 4. These can be solved with substitution or elimination to get x equals 1 and y equals 2. Therefore, the point 1, 2, 0 lies on the intersection between the two planes. Using this information and the direction vector, we can build the symmetric equations of the intersecting line x minus 1 over 5 equals y minus 2 over 11 equals z over 7. If you have further questions on this or any other math topic, or wish in-person tutoring, please consult the Academic Support Coordinator on your respective campus. Thank you, and good luck with your studies.